capital C with a circle around it, and it's red, body temp. Okay, what else? What about this one, folks? pH, blood pH, pH of other tissues, pH of urine, and blah, blah, blah.
Viscosity.
Okay, what about blood glucose? And by this, I'm bracketing, I mean blood, a concentration of blood glucose. Oxygen levels. I mean, pressure. We talked about, well, you can talk about blood pH, but pressure, just partial pressures of oxygen and CO2, blood pressure, it says, all of these are body conditions, folks. And if we do blood glucose, we should do blood calcium ion levels, blood, bicarb, et cetera, et cetera, et cetera. So there's lots and lots of body conditions, but here's where those come into play. That we're going to be acting in such a way that these body conditions can be maintained. How will they be maintained? I hope is within very narrow, maximized physiologic conditions. They can be maintained within, I mean, they're fairly narrow. I'll just put narrow, because body conditions can't fluctuate too far or you die first. If your blood pH goes above 7.45, you're in real trouble. And if it goes beyond by too much, you die. Yeah? So within narrow, I'm going to say maximal, because the idea of the narrow existence of these ranges is that now your body physiology is maximized. Maximal physiologic range. Would I ever expect you to write this exact thing on the discussion of homeostasis? Absolutely not, folks. Everybody has to come up with your own definition of homeostasis. It's a struggle. Homeostasis is not just one easy little concept. You have to, if you were to be asked to bring in to your definition all that it entails, that's about what it would look like. Yeah. So, as a way to work backwards to appreciate all those things, what are the ways, I'm not sure I can ask the question to elicit the answer I want. There are two sort of, what are called mechanisms for homeostasis to sort of manifest itself. And they are
positive and negative feedback
positive
loops?
feedback mechanisms and negative feedback mechanisms. Very good. So I'm just going to abbreviate positive feedback. And instead of mechanisms, let's just use the sort of the more contemporary terminology, loop. A positive feedback loop, or that's one of the ways. There are two mechanisms or two loops for homeostasis to manifest itself. One's a positive feedback loop, and of course the other one is a negative feedback loop. And I so wish I had our overhead, but I'll at least refer to the pages in the book, folks, that, first of all, what's a feedback loop? And there's a diagram on page 9 that, in a very schematic way, just lists the 3 components to any feedback loop. There are 3 components to any feedback loop. And they are essentially, so this is a little bit of an aside, we're going to specifically talk about positive and negative, but the 3 components of any feedback loop the 3 are a receptor, what's called a control center, and the third one is an effector. I mean, it's that easy, folks, that indeed some receptor, some cell or chemical or part of a cell is sitting there going binka, 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 and just sort of got their antenna up. And if it's a thermoreceptor, what's it going to be monitoring? Temperature. And the minute the temperature goes a little too far, from the comfort zone, that thermoreceptor is going to do what? It's going to respond to the change in the temperature, and so at that point, these are the three sort of hardwired parts to our feedback loop. But of course, now we have to factor in the stimulus. The stimulus has to come, yeah? So in the case of our body temperature, it's a thermoreceptor. In the case of, let's say, pain, it's what's called a nociceptor, a different kind of receptor that responds to pain. It might be, a distension of the gut wall, and you feel that gas bubble passing through your gut, and it's painful sometimes. So there's stretch receptors, there's photoreceptors, there's chemoreceptors, there's baroreceptors, et cetera, et cetera. So the stimulus is going to be specific to whatever receptor is there monitoring that condition, yeah? And then, once that receptor fires and or sends the information forward, that information is going to be hardwired. There are structures on which these either impulses or the chemical pathways proceed, but that control center is almost always either the nervous system or the endocrine system. And I want you to do the reading to, and you can sort of say, oh, okay, I could see a pathway for either of those. But the control center has to be one of our integrating systems, and those are the two systems that kind of control and integrate all other systems, the nervous system and the endocrine system. And in some cases, they're even the same system, called the neuroendocrine system. Yeah, in a few places of the body, the structure actually belongs to both the nervous system and the endocrine system. So the idea is, and then that control center decides. I don't want to give it, like human capability here, but it reacts in such a way that the stimulus is either, that information either is going to go forward or not. So like I say, that's why it's called the control center. So you can kind of read about that. And provided there's a sufficient stimulus, it's going to go forward. So then the idea is the control center then says, okay, yeah, something needs to happen, but I need the doer of whatever effect is going to happen, like a muscle or a gland, to secrete or to contract. So the idea is, the effector then takes control and responds, and now whatever that response is, that sort of creates the new status of the condition being monitored. And if in fact that response feeds back in such a way that the output reverses the input. Whoops, I'm writing that under positive. Ooh, I better. Okay. Oh, I want it to be the same in your notes. I was in the same line, but then you wonder if you have to teach your. Sorry. Let me do this definition first. If in fact the response is that the output reverses the input, then you've got a negative feedback loop, folks. Because the negative doesn't mean that it's anything negative or bad, or it just means that whatever the effector does is called the output, right? Would y'all agree this is called the output to any system? And what was the input?
The stimulus.
Was the stimulus, okay? If in fact, in the case of body temperature control, if the sweat glands, okay, secrete sweat, and that watery sweat, the sweat itself doesn't cool you down, does it? It's not actually the sweat itself, but the sweat kind of distributes itself along your body's surface, and then by convection of air, it's evaporated away, and with the high heat of vaporization of water, you draw a lot of heat off your body. So indirectly, it is the perspiration that does that, but the whole idea is that with that evaporation and that output, that takes your body temperature down. The input was that the body temperature had gone up. I'll just put it this way, body temp had gone up. But the output is that the body temperature went down. Did the output reverse the input?
Yes.
Absolutely. So it's a negative feedback loop, folks. And most feedback loops in the body are negative. They're safe. They're really the body can be very efficient with that. It's like driving your car. If you're motoring down the road and all of a sudden your car's swerving a little bit towards the median of the road, what do? You make a small correction and it comes right back to the straight line. Or if you overcorrect and go the other way, you can make a small correction. So for small input, you can make small output, and the body says, oh, okay, this is cool. I can, pretty much maintain within my narrow, maximal physiologic limits for body temperature. Okay. If, in fact, the output reinforces the input, and I know I have a bad habit of writing over other writing, so tell me when that's not tolerable. Reinforces the input. Now, folks, we have a positive feedback loop. Positive feedback loops are inherently kind of dangerous, except when the effect that's trying to be achieved is what's called a terminal event, an event that just ends. For example, blood clotting. You cut yourself, you bleed, and we're going to go into hemostasis next quarter, but you bleed, and that's not a good thing. You can lose blood, you can, damage your blood pressure goes down, a whole bunch of things happen. So the idea is, with the blood clotting mechanism, the more of the responding chemical you get for kind of trying to seal off the cut and at least to stop the blood cells from getting out of the blood vessels, the more of that you make, the more it feeds back to the input of the initial trauma to make more of that chemical. So that feeds back to make more and more and more, and pretty soon you have what's called a clot. A weave of this final product called fibrin threads that effectively